We often perceive the universe through the narrow lens of what our eyes can see, believing that if something is invisible to us, it simply does not exist. But what if the most profound secrets of the cosmos have always been hidden in plain sight, just beyond the reach of our natural senses? What if the key to unlocking the universe's deepest mysteries lay not in the grand observatories of today, but in a simple, almost accidental discovery made more than 200 years ago by a man in a darkened room? In the year 1800, in a quiet corner of England, the British-German astronomer Sir William Herschel embarked upon a deceptively modest experiment. He was renowned for his groundbreaking observations of the night sky, his masterful telescopes, and his discovery of the planet Uranus. Yet, it was a seemingly mundane inquiry into the nature of sunlight that would, unknowingly at the time, lay the fundamental groundwork for humanity's most ambitious cosmic endeavor, the James Webb Space Telescope. Herschel took a glass prism, an instrument commonly used to split sunlight into its vibrant constituent colors, much like a rainbow. He then meticulously placed a series of thermometers across this spectrum of light, diligently measuring the temperature at each color band, from violet to blue, green, yellow, orange, and red. But then, out of sheer scientific curiosity, Herschel extended his measurements just beyond the visible red edge of the spectrum into what appeared to be empty darkness. And there, in that seemingly blank space, a thermometer registered a significant rise in temperature. This was no optical illusion. It was a clear, undeniable signal of a form of energy that was invisible to the human eye, yet carried a palpable heat. Herschel, in his profound insight, termed these unseen emanations calorific rays. Today, we know them by a more familiar name, infrared. This single, elegant experiment unveiled a hidden dimension of light, a ghost light that permeated the world around us, previously unnoticed. This discovery, made over 2 centuries ago, is not merely a historical footnote. It is the fundamental operating principle of the James Webb Space Telescope. One might naturally assume that the James Webb Space Telescope, with its colossal gold-coated mirror spanning 6.5 meters, is simply a more powerful version of a traditional optical telescope designed to capture even fainter visible light. Yet, that assumption would be fundamentally mistaken. The James Webb Space Telescope is, in essence, a direct descendant of Herschel's Hubble thermometer, an instrument designed not primarily to see visible light, but to perceive the universe through the very calorific rays he first identified. It is an infrared observatory, a colossal cosmic heat sensor, specifically engineered to gather the invisible light that constitutes a vast, unexplored portion of the electromagnetic spectrum. The ability to see in infrared is not just a technological upgrade, it is a critical necessity for unraveling the universe's most profound secrets, particularly in the realm of cosmology. Consider the vast, swirling clouds of cosmic dust that pervade galaxies. These nebulae, composed of microscopic particles akin to fine smoke, are impenetrable barriers to visible light. When we look at them with conventional telescopes, they appear as dark, opaque voids, obscuring the stellar nurseries and galactic cores within. However, infrared light, possessing longer wavelengths, can slice through these dusty veils, much like a warm hand passing through a thin curtain of fog, revealing the hidden processes of star formation and galactic activity occurring deep inside. But the true cosmological power of infrared extends far beyond piercing cosmic dust. It provides an unprecedented window into the universe's most ancient past. The universe, as we understand it, is in a state of continuous expansion, a phenomenon elegantly described by the cosmological redshift. As light from distant early stars and galaxies travels across billions of light-years to reach us, the very fabric of space stretches beneath it. This stretching effect elongates the light waves, shifting them from shorter, bluer visible wavelengths towards longer, redder infrared wavelengths. What was once visible light, emitted by the first nascent galaxies mere hundreds of millions of years after the Big Bang, arrives at our telescopes today as faint, stretched-out infrared radiation. Without the capacity to detect this specific wavelength, these primordial echoes of creation would remain forever beyond our grasp. The journey from Herschel's rudimentary thermometer to the James Webb Space Telescope is a testament to humanity's relentless pursuit of the invisible. It is a technological lineage that winds its way through unexpected historical detours. During the Cold War, the urgent need for covert surveillance spurred the development of early military night vision technology, which utilized infrared to allow soldiers to see in complete darkness, detecting the heat signatures of targets. These systems, though primitive by today's standards, represented a crucial leap in applied infrared science. Decades later, as humanity ventured into space, the true potential of infrared for astronomy began to materialize. Missions like the Infrared Astronomical Satellite, or IRS, launched in 1983, provided the first comprehensive infrared map of the entire sky, revealing previously unseen galaxies, dusty star-forming regions, and even comets. Then, in 2003, the Spitzer Space Telescope, a liquid helium-cooled observatory, launched and offered astronomers their sharpest infrared views yet, unveiling details within dusty nebulae and peering at more distant galaxies than ever before. Each of these missions pushed the boundaries of our perception, building upon the foundational principle Herschel stumbled upon. The James Webb Space Telescope, therefore, is not a sudden, singular breakthrough, but rather the culmination of a multi-generational human quest. It is the apex of a 220-year scientific odyssey to perceive a universe that has always existed just beyond the limits of our natural senses, waiting to be revealed by the subtle warmth of its invisible light. For generations, it has hung on classroom walls, adorned book covers, and ignited the imaginations of millions. The iconic image of the pillars of creation, captured by the Hubble Space Telescope in 1995, became more than just an astronomical photograph. It was a cosmic landmark, a majestic celestial portrait of towering structures of gas and dust, seemingly frozen in time, reaching into the void like ethereal monuments. It whispered of grandeur, of vast, unseen processes, yet always remained at arm's length, an opaque masterpiece. But what if those pillars were not just static sculptures? What if their seemingly impenetrable surfaces hid a turbulent, living secret? Just as a physician uses an X-ray to peer through skin and bone, revealing the hidden structures beneath, humanity has now been granted a new cosmic vision. The James Webb Space Telescope, with its revolutionary near-infrared camera, known as NIRCam, has re-imaged these very pillars of creation, transforming that familiar, two-dimensional portrait into a vibrant, three-dimensional window into the heart of stellar birth. Where Hubble saw only the majestic, swirling clouds, dark and dense, Webb's infrared eyes pierce through the cosmic smoke, revealing the untold story that lies within. This is not merely an aesthetic enhancement, it is a fundamental shift in our ability to witness creation itself. The central revelation from Webb's re-imaging is startling. A multitude of newly formed stars, previously completely hidden from our view. These nascent suns appear as brilliant red orbs, often adorned with characteristic 8-pointed diffraction spikes, scattered throughout the structures of gas and dust. They are not on the surface. They are inside the pillars, like precious jewels embedded within ancient rock. The Hubble image showed us the walls of the nursery. The Webb image takes us directly into the crib, where the universe's newest inhabitants are taking their first fiery breaths. We are witnessing the very process of star birth in an almost real-time cosmic diorama. These nascent stars, known as protostars, are actively gathering mass from their tumultuous surroundings, gravitationally drawing in the vast quantities of gas and dust that make up the pillars. This accretion process fuels their growth, slowly building them into the colossal, incandescent furnaces they are destined to become. To truly understand this dynamic process, astronomers engage in a form of cosmic archaeology. They meticulously analyze the light emitted by these embryonic stars, using sophisticated instruments to decipher the chemical composition and the precise dynamics of the colossal clouds from which they are forming. Every spectral line, every flicker of infrared light, tells a story about the temperature, density, and chemical makeup of these stellar cocoons. As Klaus Pontoppidan, a distinguished scientist from the Space Telescope Science Institute, which plays a pivotal role in processing these extraordinary images, has underscored, this new perspective is far more than just a prettier picture. It represents a quantum leap in our comprehension of the stellar life cycle. We are no longer observing a distant, static, celestial scene. We are immersed in a dynamic, living laboratory where stars are born, evolve, and shape their immediate cosmic environment. The once opaque pillars of creation are now transparent, revealing the intricate dance of matter and energy that fuels the formation of solar systems. This extraordinary vision has unlocked secrets that lay hidden for eons, challenging our prior assumptions and paving the way for unprecedented discoveries about the very genesis of light in the universe. For decades, humanity believed it had charted the cosmos's infancy, sketching a grand timeline of the universe's evolution since its fiery genesis. This cosmic blueprint, known as the Standard Model of Cosmology, and more specifically the Lambda CDM model, has served as our guiding star, a robust framework that has explained countless astronomical observations. It painted a picture of a gradual, almost stately progression. After the Big Bang, the universe was a homogeneous, featureless soup, slowly, incrementally giving rise to the first stars, and then, over hundreds of millions of years, these stars would coalesce into small, clumpy, and relatively dim protogalaxies. These nascent structures, according to the model, would then painstakingly grow, through gravitational attraction and countless mergers, to become the vast structured spiral and elliptical galaxies we marvel at today, a journey spanning billions of years. This was the accepted narrative, the cosmic growth chart we thought we understood. But then, the James Webb Space Telescope turned its unparalleled infrared eyes to the deepest corners of the cosmos, looking back across light years and eons to the universe's earliest moments. And what it revealed shattered that carefully constructed timeline, presenting an enigma that has astronomers scratching their heads. The telescope's initial deep-field observations did not show the expected faint, scattered embers of nascent galaxies. Instead, they revealed something profoundly puzzling, almost audacious in its brilliance. Galaxies like Glass Z13 and Sears 93316, observed as they existed when the universe was incredibly young, a mere 300 to 400 million years after the Big Bang, appeared far too bright, far too massive, and astonishingly, far too well-structured for their tender age. This was akin to discovering fully formed skyscrapers in a city that, according to all engineering principles, should still be laying its foundations. This discovery is not just an intriguing anomaly, it is a profound scientific mystery that strikes at the very heart of our cosmological understanding. As astronomer Rohan Naidu, a leading voice from the Harvard-Smithsonian Center for Astrophysics, eloquently articulated, these findings were described as potentially breaking our established understanding of early galaxy formation. It is a bold statement, but one born from undeniable evidence. To grasp the enormity of this challenge, we must first understand how astronomers measure cosmic distance and time, a feat achieved through a phenomenon called cosmological redshift. As the universe expands, the light emitted by distant galaxies is stretched, shifting its wavelengths from the shorter, bluer end of the spectrum towards the longer, redder infrared. The greater the redshift, the further away the galaxy, and, critically, the further back in time we are seeing it. It is as if the universe itself acts as a cosmic speedometer and time machine, allowing us to accurately pinpoint the age of these primordial structures. With this cosmic yardstick in hand, the observed brightness and the surprisingly advanced structure of these early galaxies create a major cosmological conundrum. According to the lambda CDM model, galaxies of such immense size and organized form should simply not exist at a time when the universe was only a few % of its current age. They are too mature, too grand, too luminous for their infancy. Their very presence challenges the rates at which matter coalesces, stars form, and galaxies assemble in the early universe. This unexpectedly rapid and brilliant emergence of complex structures in an infant universe has been dubbed the impossible dawn. It is a dawn that suggests the first light of galaxy formation flared much faster and more intensely than anyone had dared to predict. This radical new evidence compels theorists to fundamentally reconsider the initial conditions, the growth rates, and perhaps even some fundamental physics that our prevailing cosmic model has long taken for granted, forcing us to ask, how did the universe grow up so fast? The cosmos, as revealed by the James Webb Space Telescope, had laid bare a profound challenge. Galaxies that should have been mere infants, small and dim, were instead fully formed giants, shining with a brilliance that defied our long-held cosmic timelines. This was the impossible dawn, a galactic growth spurt that begged a fundamental question. How did they grow so vast, so fast, in such an impossibly short span of cosmic time? To solve this cosmic riddle, scientists had to pivot. The answer, it turned out, lay not just in the grand scale of cosmology, but in the intricate dance of the smallest particles, a profound shift towards the realm of astrochemistry. This is where another of the James Webb Space Telescope's extraordinary instruments steps into the spotlight: its spectrographs. Consider them cosmic prisms, far more advanced than the simple glass Herschel used over 200 years ago. These instruments do not merely capture light, they dissect it, splitting the faint glow from distant galaxies into its constituent wavelengths, much like a barcode reveals the contents of a product. Every atom and molecule in the universe leaves its unique signature in this cosmic spectrum, allowing scientists to determine the chemical composition of stars, gas, and dust across billions of light-years. And what these cosmic prisms revealed was nothing short of astonishing. Within the very first billion years of the universe's existence, in galaxies still reeling from the aftermath of the Big Bang, the James Webb Space Telescope detected the unmistakable fingerprints of complex organic molecules. These were specifically polycyclic aromatic hydrocarbons, often referred to by their acronym PAHs. Perhaps you are familiar with PAHs from a more terrestrial context. They are carbon-based molecules often found on Earth as products of incomplete combustion, like the soot from a burning candle or the exhaust from an engine. For decades, the prevailing scientific wisdom, held by brilliant minds like Olivier Bernet and his dedicated team at the French National Center for Scientific Research, was that such large, intricate carbon structures, often considered the very precursors to life's fundamental building blocks, would require far longer to assemble in the universe's infancy. Their presence in these nascent galaxies was, frankly, an anomaly, a chemical ghost appearing millennia before its expected arrival. But what if these chemical ghosts were not just an anomaly, but a crucial piece of the puzzle, a hidden ingredient in the universe's first cosmic recipe? A groundbreaking hypothesis suggests that the premature appearance of these polycyclic aromatic hydrocarbons could be the key to unlocking the mystery of the impossible dawn galaxies. The secret lies in their remarkable efficiency. Unlike simple hydrogen and helium, the primary constituents of the early universe, PIHs are incredibly effective radiators of heat. Think of it like a microscopic cooling system woven into the fabric of gas clouds. As these vast nebulae of primordial gas begin to collapse under their own gravity, they heat up dramatically. If they cannot shed this excess energy, their collapse slows down, hindering the rate at which new stars can form. Here is where the polycyclic aromatic hydrocarbons become indispensable. These molecules act like tiny, highly efficient cosmic radiators. They absorb energy from the hot gas and then re-emit it at longer infrared wavelengths, effectively cooling the gas cloud much faster than if it were composed solely of basic hydrogen and helium. This rapid cooling allows the gas to collapse more quickly, reaching the densities and temperatures necessary for star formation at an accelerated pace. More efficient cooling means more rapid collapse, which in turn means stars burst into existence with unparalleled speed and in greater numbers. This sudden burst of stellar formation would then rapidly build up the mass and luminosity of these early galaxies, giving them the impossible brilliance and structure that the James Webb Space Telescope observed. This astonishing discovery creates an unexpected and profound link between the seemingly mundane chemistry of soot and the grand, majestic formation of the very first galaxies. It paints a radically different picture of the early universe. No longer a pristine, simple expanse of only hydrogen and helium, the infant cosmos now appears to have been quickly seeded with a complex cosmic recipe, a rich brew of molecules that supercharge the process of star and galaxy formation. The presence of these polycyclic aromatic hydrocarbons provides a compelling physical mechanism, a chemical engine, for the rapid, impossible observations that continue to reshape our understanding of how the universe grew up so fast. What if the most spectacular cosmic photographs you have ever seen are not, in fact, photographs at all? When the James Webb Space Telescope unleashed its initial torrent of breathtaking images upon the world, depicting swirling nebulae, distant galaxies, and the intricate dance of starbirth, a natural question arose in the minds of millions. Is this what it really looks like? The answer, both surprising and profoundly enlightening, is that these stunning portrayals are not mere snapshots captured by a cosmic camera. Instead, they represent something far more intricate and revealing. They are sophisticated data visualizations, a powerful fusion of cutting-edge science and meticulous artistic interpretation. To truly appreciate these celestial masterpieces, we must look beyond the conventional understanding of a photograph. A traditional camera captures visible light, much like our own eyes. But the James Webb Space Telescope, designed to see the universe in infrared, registers light that is entirely invisible to the human eye, light that reveals secrets hidden behind cosmic dust and stretches across unimaginable distances. This raw data, collected by Webb's various infrared detectors, arrives back on Earth not as vibrant, full-color images, but as monochromatic grayscale information streams, often appearing as little more than hazy, pixelated smudges to the untrained eye. It is here that the extraordinary process of translation begins, transforming invisible wavelengths into observable beauty. At institutions like the Space Telescope Science Institute, dedicated science visualizers, minds like Joe DiPasquale and Alyssa Pagan, embark upon a process that is as much art as it is rigorous science. They are the cosmic cartographers, taking the raw, invisible light data and meticulously translating it into the full-color images that captivate and educate the public. This painstaking work involves assigning visible colors to different infrared wavelengths, allowing us to perceive structures, chemical compositions, and physical processes that would otherwise remain entirely hidden. The choices made in this translation are not arbitrary aesthetic whims. They are deeply rooted in scientific logic, following a system known as chromatic ordering. This chromatic ordering dictates a precise logic. The shortest infrared wavelengths detected by the telescope are typically assigned to the color blue, medium wavelengths to green, and the longest infrared wavelengths to red. This systematic approach is a vital scientific tool, meticulously designed to make distinct physical processes and specific chemical elements visually discernible within the vast cosmic tapestry. For instance, the color red within these images often highlights the presence of glowing dust and molecular hydrogen, key ingredients for star formation, signaling regions where new suns are actively coalescing from primordial clouds. Blue, on the other hand, might reveal hotter, more energetic phenomena or the presence of specific elements that emit shorter infrared light. To grasp the power of this method, consider a familiar parallel in the medical world. When a doctor needs to examine the intricate structures within the human body, they do not rely solely on what the eye can see. Instead, they utilize advanced imaging techniques like magnetic resonance imaging, or MRI, or positron emission tomography, known as PIT scans. These technologies also capture data that is invisible to the naked eye, magnetic fields, radio waves, or emitted positrons, and then translate that information into false color images. These medical scans, much like the images from the James Webb Space Telescope, use color not for artistic flair, but as a diagnostic tool, allowing experts to differentiate between bone and tissue, healthy cells and diseased ones, revealing biological structures and processes that would otherwise remain undetectable. This understanding fundamentally demystifies the stunning images we see from the James Webb Space Telescope. They are not simple snapshots, nor are they digitally enhanced fictions. Instead, they are rich, multi-layered maps of data, painstakingly rendered to allow both scientists and the public to interpret the complex physics of the invisible universe. Each brilliant star, each swirling nebula, each distant galaxy in these images is a carefully constructed visual representation of invisible light, carrying with it the profound secrets of cosmic evolution, waiting for us to decipher its hidden language. How does one redraw a map of the universe when the very edges of what we thought we knew have been fundamentally shattered? Our journey through the cosmos with the James Webb Space Telescope has been one of profound revelations, each observation peeling back another layer of cosmic mystery. It began with a 200-year-old pursuit, rooted in Sir William Herschel's deceptively simple experiment, a quest to perceive the invisible warmth of infrared light, a ghost beyond the red end of the spectrum. That singular leap of perception allowed us to gaze into the heart of stellar nurseries, piercing through the opaque veils of cosmic dust in the iconic pillars of creation, revealing countless nascent stars bursting into being, previously hidden from our view. Yet, this unprecedented clarity immediately confronted us with a universe whose childhood was far more precocious, far more brilliant than any model had ever predicted. The revelation of massive, well-structured galaxies existing mere hundreds of millions of years after the Big Bang, an impossible dawn, fundamentally challenged the very timeline of cosmic evolution we had meticulously constructed over decades. Then, deep within those primordial galaxies, the telescope's sensitive spectrographs uncovered a potential clue, a surprising element in the ancient chemical recipe of the cosmos: complex organic molecules like polycyclic aromatic hydrocarbons, long thought to be much later arrivals. These microscopic radiators, perhaps, allowed gas clouds to cool and collapse at an accelerated rate, supercharging star formation and offering a potential solution to the perplexing speed of early galaxy growth. And throughout this astounding voyage, we learned to interpret the new language of these revolutionary images, understanding them not as simple photographs, but as intricate, multi-layered data visualizations, where color itself becomes a scientific tool, painting the invisible physics of the universe for our comprehension. The true significance of the James Webb Space Telescope, then, is not found in providing neat, definitive answers. On the contrary, its most profound contribution lies in its power to fundamentally shatter our previously tidy cosmic timeline, revealing an early universe that is far more complex, dynamic, and even chaotic than we ever dared to imagine. It is as if we were handed a perfectly drawn map of a continent, only to discover, upon closer inspection, that entire mountain ranges and vast oceans were missing, replaced by blank spaces where unknown territories should be. The telescope has not completed our cosmic map. Instead, it has exposed the glaring inaccuracies and vast blank spots on our old one, and it has handed humanity a new pencil, urging us to begin sketching a completely new, far more exciting, and profoundly unfinished one. So, where do we go from here? What new frontiers of understanding does this impossible dawn now force us to confront? Scientists across the globe are currently exploring several major, competing hypotheses, each attempting to reconcile these extraordinary observations with the fundamental laws of physics. One leading line of inquiry focuses on our understanding of dark matter, the enigmatic, invisible substance that is believed to constitute roughly 27% of the universe's mass, 5 times more abundant than the ordinary matter that makes up everything we can see. Dark matter is thought to be the gravitational scaffolding upon which galaxies form, its invisible halos providing the initial wells of gravity that draw in gas and spark star formation. Could it be that our models of dark matter, or its distribution in the very early universe, need significant revision? Perhaps its gravitational influence was even more efficient, or its structure more conducive to rapid galaxy assembly than our current simulations suggest. This would mean a subtle but crucial tweak to the very foundations of our cosmic architecture. Another compelling hypothesis delves into the nature of the very first stars, theoretical entities known as population 3 stars. These would have been born from the pristine hydrogen and helium left over from the Big Bang, before the universe was enriched with heavier elements forged in stellar furnaces. According to existing models, these first stars were likely massive, perhaps hundreds or even 1,000 times the mass of our Sun, but their exact properties and their efficiency at producing and dispersing heavier elements remain subjects of intense debate. What if these population 3 stars were even more massive, more numerous, and far more efficient at burning through their fuel and exploding as supernovae than we previously thought? These cataclysmic explosions would have rapidly seeded the early universe with the heavier elements that are crucial for the formation of complex molecules like polycyclic achromatic hydrocarbons, accelerating the cooling of gas clouds and allowing for an incredibly swift cascade of star and galaxy formation. Such a scenario would provide the raw materials and the high-octane fuel needed for galaxies to grow to such immense sizes in such a startlingly short period of cosmic time. The James Webb Space Telescope has ushered in an era where our certainties are replaced by exhilarating questions. It has not provided the final word on the universe's past, but rather, it has revealed that the grand narrative of our cosmic origins is far more intricate, more surprising, and infinitely more compelling than we could have ever imagined. The cosmos, in all its perplexing grandeur, continues to unfold its secrets, inviting us to delve deeper into its mysteries.